So, there's this huge news coming out of Stanford University that might just be the key to unlocking the real world-changing power of quantum computing. Let's dig into what this breakthrough is and, why it's such a big deal.
I mean, just imagine for a second. What if we had a computer so incredibly powerful it could chew through problems that our best supercomputers today just can't touch? We're talking about tasks that would take thousands of years, done in a couple of hours.
Yeah, this isn't science fiction anymore. This is the incredible promise of quantum computing. It's a technology that scientists are racing to build as we speak. But for all that amazing potential, there's been one giant roadblock standing in the way.
And that roadblock? It's all about scale. See, building these things is ridiculously hard. And to really get why, we have to start with the most basic piece of the puzzle, the very building block of all quantum information.
It all comes down to the qubit. You know how a normal computer has bits? Well, a quantum computer has qubits. And while those names sound kind of similar, what they can actually do, well, they're worlds apart.
So, look on the left there. That's your classic bit. Think of it like a light switch, right? It's either off, that's a 0, or it's on, a 1. Simple. But now, look at the qubit on the right. Thanks to the wonderfully bizarre rules of quantum mechanics, it can be a 0, it can be a 1, or, and this is the part that changes everything, it can be both at the exact same time.
This wild ability to be in multiple states at once is called superposition, and it's basically the secret sauce for all this quantum power. One of the researchers, John Simon, has a great analogy for it. A classical computer goes through possibilities one by one by one. But a quantum computer? It's more like a pair of noise-canceling headphones. It compares tons of combinations all at once, amplifying the right answer and just canceling out all the wrong ones.
Okay, so if these qubits are so powerful, what's the holdup? Why don't we have massive quantum computers everywhere? Well, the problem isn't just having qubits. It's being able to read the information out of them quickly and reliably.
And here is the core of that challenge. The quantum information is stored in a single atom. To read that info, you have to catch the tiny little particles of light, photons, that the atom gives off. But here's the thing. Atoms are terrible at this. They spit out light really slowly, and they spray it randomly in every single direction. It's like trying to catch one specific raindrop during a hurricane. Now imagine trying to do that for 1 million raindrops at the same time. Yeah, it's been pretty much impossible.
Like lead researcher John Simon says, speed is absolutely everything here. You have to read that qubit before its super fragile quantum state just collapses into nothing. The problem was, there was no practical way to do that on a large scale, until now.
And this brings us to the breakthrough. The Stanford team has created a brand new kind of light trap and was designed to solve this exact problem. They built something called an optical cavity. The best way to think about it is like a tiny, perfectly engineered chamber made for one single atom. Its entire job is to trap and guide every last particle of light that atom emits, making sure none of that precious quantum information gets lost.
So what makes this new cavity so different? Well, the genius of it is in a completely fresh approach to controlling light.
The old way, you see on the left, was kind of like a funhouse mirror. You're just bouncing light all over the place and hoping it interacts. It was super inefficient. But the new design on the right, it's so much smarter. It's more like a magnifying glass. It uses these tiny microlenses to focus light with unbelievable precision, right onto the atom. It makes the whole process fast, direct, and way more effective.
So the result is a system that's just incredibly good at pulling that quantum information out of each atom. But, and this is the real game changer, because each one of these microlenses is its own self-contained unit, the whole design is modular. It's literally built to be scaled up from day one.
So, what does this actually mean for the future? Well, this could be the thing that finally unlocks the path to the holy grail of quantum computing, a 1,000,000-qubit machine.
And hey, this isn't just a theory on a chalkboard. The team has already built a working array of 40 of these optical cavities. Next up is a bigger prototype with over 500. This gives them a clear, scalable roadmap to get from today's experiments all the way to that goal. Quantum networks with 1,000,000 qubits, or even more.
So what in the world could you do with a 1,000,000-qubit computer? Well, you could accelerate drug discovery, designing new medicines in a fraction of the time. You could design revolutionary new materials, literally from the atom up. You could break today's most complex encryption codes. You could even build telescopes powerful enough to see the atmospheres of planets orbiting distant stars.
And as first author Adam Shaw points out, this technology is about so much more than just computers. By learning how to control light at the level of a single particle, we fundamentally transform our ability to see everything, from the tiniest things happening inside our bodies to the biggest structures in the universe.
So this breakthrough doesn't just promise us better computers. It opens a brand new door to observing reality at its most fundamental level, which of course leaves us with one pretty mind-blowing question. Once we can finally see the universe at the quantum scale, what secrets is it going to reveal?